Okay, hello. So today we are going to shift from what we were doing earlier, which is about how to describe diffusing particles in terms of diffusion equation, understand the properties of those equations, generalizing the diffusion equation to various more complex situations. For example, diffusion in the presence of some net flow, diffusion when you have an arbitrary initial condition of some densities that you specify and you want to ask what is the density at some later time. So now what we want to do is to think a little bit about how do we describe the systems in thermal equilibrium. So we'll start with discussing a little bit of thermodynamics, and the idea will be to get from thermodynamics to statistical mechanics. Statistical mechanics is a set of rules for understanding the behavior of large numbers of particles. So in a sense, all of what we were doing until now, which is the description of the diffusion equation, the probability distribution governing particles which diffuse, was an example of statistical mechanics. But we're going to look at an earlier, sort of even a prior version to what the problem that we were doing, which is to discuss equilibrium systems. The diffusing particle and the calculation that we did for the diffusing particle is not a system in equilibrium because the probability distribution changes with time. Here we want to look at systems which have settled down so that any probability distribution that I might use to describe them is independent of time. So now the question is, what is the form that distribution will actually take? So in order to do this, we should start at a more basic level and ask, what is it that these theories can describe well? What is the ways of testing these ideas, and what do they mean for our understanding at different levels when we think about biological systems? So let's start thinking about systems in thermal equilibrium. So one example that I like to use is the example of a coffee cup. When you get coffee from upstairs and you put it on the table, that coffee is at the temperature of the pot in which it was made. After some time, that coffee begins to cool down, and if you wait for something like a few hours, that coffee becomes the temperature of the room. After that, the temperature does not change, and it now, provided you cover it up so that particles are not allowed to evaporate away from it and so on, that cup of coffee has now forgotten the state at which you started out with. That is to say, if I had 2 cups of coffee that were prepared at different initial temperatures, one was much hotter than the other, and I left them on the room on a table and I waited long enough time, both of them would reach a state in which they would not change anymore, and beyond that the properties of both of these are essentially the same. So an essential of describing a system in thermal equilibrium, so let me just qualify that further. So systems in thermal equilibrium, their properties don't change in time. So the properties don't change in time, and these properties are independent of history. So systems of physical systems of a large number of particles with the property that the current state is independent of how they were prepared initially, and therefore these properties don't change in time. Such systems are said to be in thermal equilibrium at some temperature, let us say T, and we want to understand how to describe them best. Okay. Let's now begin to make the distinction between different types of variables that we can use to describe a system. Suppose my system is, I have a box here of fixed volume, and I have a number of particles inside that box. So there are n particles, and there is a volume which is V. These particles here have some energy, they're moving around, they're interacting with each other. So a quantity called U I can also define, which is the energy of this thermodynamic system. So a large number of particles confined to a fixed volume and with a fixed energy. So, I am not pushing energy into the system. When particles collide off the wall, they collide elastically. So, the energy with which they went in is the same as the energy with which they came out. If they were losing energy to the system, then they would gradually slow down. If the wall, for example, kept sucking up some energy from these particles as time went on, then the system would settle down. Its state would still be evolving. But when I think of a system like this, of a bunch of particles moving around, interacting with each other in such a way that their energy remains fixed, I am talking about a particular thermodynamic system in which I fix the number of particles, the volume, and the energy. These are somewhat special parameters because they are what are called extensive parameters. And the simplest way of understanding an extensive parameter is to say, let me take two identical copies of the system and let me place them next to each other. So here is one, and next to this I might have put my other little box. How do these parameters that describe the composite system or the joint system, what are they functions of? Well, the answer is that the composite system now has twice the number of particles, it has twice the volume, and twice the energy, because I have taken two identical copies and put them next to each other. So these are called extensive parameters because these variables or these parameters add up when you take identical copies of the system and put them together. Okay? These are to be distinguished from parameters which you might call intensive parameters. One example of an intensive parameter is the temperature. So if I take two identical systems and put them next to each other and I ask, what is the temperature of this combined system? The answer is it's still the temperature of these individual systems. It's not T plus T, which is 2T. It's just T again. So the temperature is an example of an intensive parameter as opposed to an extensive parameter, which are these quantities over here. Okay? So now we have some understanding both of intensive and extensive parameters. The other thing that we need to know whenever we talk about thermodynamics is, these are ways of thinking about large systems. The rules of thermodynamics work specifically for large systems. They don't work for systems of one or two particles at a time. When we think about the behavior of individual particles, we should be really using behavior of statistical mechanics. But what thermodynamics says is that even though you may take a very large number, say 1 mole of particles inside here, 10 to the 23 particles, for many practical questions that you can ask about the system, you don't need to specify what each one of these little variables inside, each one of these little particle coordinates inside is doing. You only need a relatively small number of variables that describe the system. For example, for simple system, that is to say particles moving around interacting with each other, but without any electric fields acting on the system, without long range interactions between these particles, you only need these three variables, the number of particles, the volume, and the internal energy U, to describe the system. What this says is, if I want to talk about large systems in thermodynamic equilibrium that are not very complicated systems, they don't have particles that are charged, for example, then I only need a small number of variables to describe them. So one nice example is if you go and try to order ethyl alcohol from a chemist's shop, there are a bunch of bottles that are stacked on the shelf. You don't say, I want this bottle and not that bottle because these atoms are, the behavior of this bottle is different from the behavior of that bottle. That's not true. All I need to say is I need a volume which is 400 ml, which contains automatically, given a fixed density, a certain number of particles. And they're all in the same condition there. So there's no reason for their energies to be very different between these individual situations. They're all in equilibrium with the outside. So instead of specifying the location and momentum of every individual particle in that bottle of ethyl alcohol, I've just reduced my requirements to a very simple. I just say, give me a fixed volume and therefore a fixed number of particles from your shelf, and therefore which is at fixed energy because it's in equilibrium with its surroundings. So the fact that you can describe very complicated systems with lots and lots of degrees of freedom by very small number of variables is in itself very interesting. Now you can ask, have I forgotten any other variables here? Should there be something like, for example, the color of all the particles or any other attributes that I might want to put in? So the answer would be that you calculate the properties assuming these, calculate the thermodynamic properties of the system assuming a certain set of variables, and then whether it is a complete set or not will reflect in the thermodynamics. If you have not done it correctly, then the thermodynamics will make certain predictions that will be wrong. Okay, so the test of the thermodynamic theory is whether all of these parameters, that are all of these extensive variables, have been included correctly. He said it makes certain predictions which you can then test. Okay. So now we have described extensive variables, intensive variables. There are other intensive parameters that I will tell you about. There's one thing called the chemical potential, and there is a pressure as well. All of these are intensive parameters. They're related in some way to these extensive parameters here, which we will define. What is the relationship between this and this?
So what is mu?
Mu is called the chemical potential. So we will describe this. It's very important in the study of chemical reactions. And we will define what the chemical potential is and what it does and where it's useful. Okay. So now, let us consider what you might call a closed system. A closed system is one in which the energy, the volume, and the number of particles is a constant. It's not allowed to change because I constrain or put walls on the system that don't allow the energy to be interchanged, the volume to be interchanged, or the number of particles to be interchanged. So each of these individually is a constraint. By applying suitable constraints to the system, apply a suitable constraint, I can prevent it from exchanging energy with its environment, the volume, or the number of particles. The volume and the number of particles are easy because all I need to do is to put some wall there, make sure that my wall does not allow particles, and the walls cannot move, so the volume cannot change, and the walls are impenetrable, so particles cannot leave once they're inside. But to make it impossible for energy to leave is a little more complicated. And the nice example is that of a thermos bottle or a thermos flask, which is constructed essentially so that it has its two mirrored or highly silvered surfaces with a vacuum in between. So because of the vacuum and the silvered surfaces, energy passes very slowly between here. Heat, for example, passes very slowly between inside and outside. The conduction is relatively little. Heat tends to reflect off the silvered surface. And because of that, stuff that you put inside here can remain warm for a longer time, which is the basic idea behind the thermos flask. Okay? So this is how you would apply a suitable constraint to keep U, V, and N from being exchanged with the environment. I can think of either saying this is a constraint or saying that it's a suitable wall that separates the inside and the outside, that permits the transfer of particles or permits the transfer of volume or doesn't permit it. Okay. So now we have said here are the variables that we are going to use to describe the system, and we have said but not made this sharper, that these are all the variables that you need to describe a system in thermal equilibrium, provided the system itself is not too complicated. So for systems that are described completely by the number of particles, the volume, and the internal energy are called simple systems. So if I think of sufficiently simple systems that are described by specifying how many particles, what volume, what energy there is, then I have specified the thermodynamics of that system. But just this isn't enough, because what I need to do is say, find a function that is, find one quantity that is a function of these that tells me a little more about the system. That quantity will play a very important part in everything that we will discuss. That quantity is called the entropy. And the entropy goes by the symbol S. So the statement is, if I tell you what is the entropy as a function of U, V, and N, I have told you many things about the behavior of this particular system. I have not told you what the entropy is. I have said there is a function called the entropy, which is a function of U, V, and N, which are all the parameters that I need to describe my system. and all of the complexity, all of the behavior of the system in equilibrium is controlled by this entropy. Okay? The entropy itself is an extensive quantity, and it's worth thinking a little bit about what entropy actually means, and we'll come back to this later when we discuss this in more detail. U, V and N are like macroscopic attributes of the system. It's a total number of particles, the total volume, etc., which completely ignores the fact that it's contained, that it consists of lots of little atoms inside it. So what the entropy does is to define the state of all of those little atoms inside. The entropy is a way of combining all of the information about the state of those little atoms into one single function here, S is a function of U, V and N. What this means will become a little clearer a little further on as we describe this in more detail. There are just some requirements for this entropy. The first is that entropy increases monotonically with the energy U. Increases monotonically means it does something like this. The larger the U, the larger the entropy. It also has to have some mathematical attributes. For example, it must be a continuous and differentiable function. So it's a smooth curve. You're not allowed to have breaks in this curve. You're not allowed to have a situation where it does this and then jumps to another value here. All of that is not allowed. Given an energy, I have an entropy here, which is a single valued function of that energy, and this function increases as I increase my energy. The fact that this increases is the fact that delta S by delta U must be greater than 0. Okay. So here are facts about the entropy as a function of the energy, which says that it must certainly do things like this. The third useful fact about the entropy is, if I have a system that is a composite system, so here is a new word here. A composite system is a system which is made up of two parts, say part 1 and part 2, and over here I might have N1, V1, U1, and here N2, V2 and U2. And these are walls that don't allow the number of particles to change, the volume to change or the energy to change. It's as though I have taken two completely enclosed systems and put them together and call this my new composite system. Okay. So for the composite system, the entropy is additive over these different parts of the system. So the total entropy is a sum of the entropy of this box plus this box. Okay. So the total entropy associated with the total energy U1 plus U2, number of particles N1 plus N2, and volume V1 plus V2 is just S1 of V1 N1 U1 plus S2 of U2 N2 V2. This is the entropy of system 2. Entropy of system 1 is a function of these parameters. This quantity, which is the entropy as a function of U, V and N, is actually so important to the discussion that it has a special name. It's called a fundamental relation. Okay. So far, all we've been really doing is introducing various pieces of terminology. First, one phrase was extensive parameters, the other phrase was intensive parameters. We defined temperature, chemical potential, etc. as quantities that were intensive parameters, but we didn't say what they were yet. Then we introduced the word, we introduced the word fundamental relation, we introduced the word constraint or wall, we introduced the concept of entropy as describing a system, and now we've introduced the word composite system over here. Yeah. No, the relationship between the entropy as a function of u, v and n is called a fundamental relation. This just says that if I have two systems with subsystems here, both of them described by the same fundamental relation, then the total entropy is just the sum of these two individual entropies. So here, let me state what is sometimes called the fundamental problem of thermodynamics, and it's going to be stated in a somewhat different way from which it's obvious. And that way is the following. It says that the fundamental question or the fundamental problem of thermodynamics. Just a sec. Yeah.
We were able to add the entropies because UV and N are extensive quantities by themselves. If entropy was not a function of all extensive, would we still be able to add entropy?
No. So this is in a sense you can think of this as a definition, saying that if I have a composite system, one part here and one part here, then I will define my entropy to be additive over these systems. In a deep sense, it's a definition, and this is a way of a set of postulates that are consistent with what we know about nature. So the fact that entropy is additive is a postulate. Entropy as written as a function of its extensive variables is a postulate of this theory. Okay, and we'll understand what it means a little later, what exactly this says.
So also in the other case that those systems were mixed up, right?
So here we are not mixing them up, we are not allowing them to exchange anything so far. We are just saying what is the meaning that you will assign to an entropy of one system 1 and system 2. The meaning that you will assign is that the total entropy is just the sum of these individual entropies. That's a definition of how entropy is additive over any sort of subsystems. And if you can do it over two systems here, if I have any number of subsystems, the total entropy of the system is just the sum of the entropy in each of these subsystems. Why it's defined like that will become a little clear as we go on. Okay. So the fundamental problem of thermodynamics is what is the final state of the system, of the composite system in this case, when an internal constraint is removed. This is a somewhat complicated way of defining things. So let me just tell you what it means. So here we had a subsystem 1 and a subsystem 2. Right now they can't talk to each other, they don't communicate at all. So it's as though there is some internal constraint. There is an external constraint, which is that they don't talk at all to the environment around them. They're completely insulated from that. But there is also an internal constraint that prevents this from interacting with this, either by exchanging particles or by exchanging volume or by exchanging energy. Okay. So this is a composite system with an internal constraint. We understood what constraints were. An internal constraint for a composite system is something that prevents the exchange of n, v or u between different parts of the system. For simplicity, we will consider this case of only a simple composite system with just two parts to it. So now the question is, suppose I now allow energy to flow from here to here, from anywhere to anywhere. What is the nature or what is the behavior of the final system? So we will have to decide what to do and what the definitions we developed so far will tell. But the point I want to make here is that this is, even though it may not look like it, almost all questions in thermodynamics can be written in this fashion. For example, if I had my hot cup of coffee and I put it in a thermos flask, I am saying that it cannot exchange energy with its environment. Okay, so that is my constraint. I can think of all of the environment as some other part of the system, and my coffee cup encased in the thermos flask as the part of the system that I am interested in. If I remove that constraint by transferring it from a thermos flask into something like an ordinary coffee cup, now it can exchange energy with its environment. In a completely ideal thermos flask, that system would remain exactly as it is, as hot as it was it started off in the beginning. But once I transfer it to something with which it can exchange more readily energy with the environment, that coffee cup will begin to cool down. So its state has changed from beginning to end. The question is, how do I predict that final state? And that's a question that is essentially asked here. What is the final state of the composite system when you remove an internal constraint, when you allow the relaxation of an internal constraint? Oops. So the answer to that, the answer to the fundamental problem of thermodynamics is that the system chooses a state such that the entropy is maximized across the manifold of constrained states. Okay? So this is what that means. This says here is a system that you started out with, and maybe this had energy U1 and this had energy U2, and this was system 1, this was system 2. And now I allow it to change energy. Okay? So the entropy S here, the total entropy is S of 1 plus S of 2. But this is S of 1 as a function of U1. This is S of 2 as a function of U2. Okay? I'm just explaining that to you. So that's a slightly more technical language, but I'll tell you exactly. It means something very simple. Okay? So the manifold of constrained states is all states that are obtained by varying the amount of energy between this and this. For example, one such state might be 0 energy here and U1 plus U2 energy here. Okay? Another possible state might be 0 energy here and U1 plus U2 energy here. A third possibility might be U1 plus U2 divided by 2 here and U1 plus U2 divided by 2 here. Or it could be U1 divided by 7 plus U2, and this would be U2 6 by 7 times U1. So the total energy would add up to U1 and U2. It's some division. So this describes a whole bunch of states with the same total energy, but different ways of dividing this energy between the two subsystems. So this is the manifold of constrained states, because each one of these states I can realize by imposing a specific constraint. For example, if I can put all the energy here, no energy here, and put a constraint that prevents energy interchange from here to here. So this is a state that can be realized by putting a specific constraint. I can realize this state here by putting all the energy here, no energy here, and putting a wall that prevents the interchange of energy. That would be another state. So all of these constrained states I can realize by starting the system off in a particular way and putting a constraint. Okay. So this is just one example of the large number of states. But I have some specified U1 here and some specified U2 here. But you will agree that in general, if I allow them to transfer energy between each other with only the restraint or the restriction that U1 plus U2 is a constant, then all of these different states are allowed. Is that correct? So now the instruction is, for each one of these, compute S and S. So here this would be S for system 1 at energy 0, and this would be S for system 2 at energy U1 plus U2. Over here I would write S of system 1 at energy U1 plus U2, plus S of system 2 at energy 0. Here I would write S of system 1 at energy U1 plus U2 by 2 plus S of system 2 at energy U1 plus U2 divided by 2. And what I've used in order to write this is just the fact that if I have a composite system, the entropy is just the sum of the entropies of those individual systems. Okay? So now the statement, the meat of the statement lies here. Entropy is maximized over the manifold of constrained states. That is to say, there is one particular division of the energy that corresponds to the maximum value of this function.
But the sum is constant, right?
Because I've not told you what this function is, no? This could be an arbitrarily complicated function here. So you can try that. Suppose S equal to U squared, energy squared. S of U is U squared. Okay? So depending upon what is the nature of this function S, which once I tell you the fundamental relation, you will be able to write it down. What you're instructed to do here is, once you allow these two systems to interchange energy, then any one of these states is realized. Any one of these divisions of energy between these subsystems is realized. The one that is chosen physically is the one which corresponds to maximum entropy. Okay.
This is only in the case of energy is the parameter which is changing.
This is the case where you allow energy to be interchanged between these two. But that's the next question. That first of all, we started off by saying I have S as a function of U, V and N. But then I said S has certain specific properties with respect to U. And all those properties were listed here. Entropy increases monotonically with energy. It's a continuous differentiable function. That means I can also invert this function to get U as a function of S, V and N. Here I have treated my energy as my dependent variable, as my independent variable, and the entropy is a dependent variable. It depends upon what I specify to be my U. But because the relationship between S and U is so simple, I can go back and write U in terms of S, V and N.
Here S of U1 plus U2 is not equal to S of U1 plus S of U2?
No, not necessarily. Here, depending upon how here this is true. The total entropy is always the sum of the entropy here and the entropy here. But the entropy here depends upon what is the value of the energy here, and this depends upon what is the value of the energy here. It may happen that the entropy is maximum if I put no energy here and all the energy here. It may happen that the entropy is maximum if I put equal amounts of energy between here and here. I don't know that a priori. I need to know what is S in order to make this judgment about which one is the largest.
When we say about manifold of constrained states, we only consider the parameter of energy.
In this case, we will later generalize it to allow the volume to change and the number of particles to change. So this is a particularly simple situation where I said you have a subsystem and now I allow energy to interchange between the two sides. But in principle, I could also allow for the fact that the wall that was initially here can now move here. That means now the volume of this has changed to V plus dV, and the volume of this has changed to V minus dV, whatever, V2 minus dV, V1 plus dV. So this is now as though volume has been interchanged between the two subsystems with the constraint that the total volume is fixed. I can also make little holes in the wall and allow the number of particles to change, because now particles can move from here or from here to here. These will all give us different types of conditions. And again, there is a similar expression here, that if I allow the volume to change, keeping everything else fixed, then the system chooses the state corresponding to maximum entropy. So now let us introduce one definition that is going to be important to us. And that's a definition that says delta S by delta U at fixed V and N is defined to be a quantity called the temperature, sorry, the 1 over the temperature. Let me just write that a little more neatly. Okay. So this is right now a definition. It says there is a quantity called the temperature, which is defined by the derivative of S with respect to U. Already I know the delta S by delta U has to be positive. That says that the temperature has to be a positive number. It's because of S is a smooth and differentiable function, certainly this derivative should exist. Therefore, the temperature can be defined everywhere. Anywhere I can define S as a function of U, I should be able to define a temperature. So this is my definition of a temperature. And now let us see whether or not it is consistent with what we understand about a temperature. Okay. So if we do that, let us take our old friend, the composite system, and let us say there is some energy U1 here and U2 here, and let us say a certain amount of energy du passes from one to the other. Okay. So the condition is that the entropy must be maximum in that final state. So let me look at the final state. So in the final state, ds must be 0. ds being the first derivative of the entropy. You cannot increase the entropy further by transferring energy from any part of the system to any other part of the system. Okay. So ds equal to 0 implies that delta, first of all, d of S1 plus S2 equal to 0, because S is just S1 plus S2. S is always additive over systems 1 and 2. Is that clear? So this is delta S1 by delta U, and S1 has say U1, V1 and 1, plus delta S2 by delta U of U2, V2 and 2 times du, let me say du1, this is du2 must equal 0. So here I am taking a derivative of each of these with respect to each other, and this is ds is delta S by delta U times du. Okay. Let me just write that. ds is delta S by delta U times du, but now this breaks up into these different parts here. S is S1 plus S2, so it has two different parts to it which add to it. So I keep various things constant when I take this derivative. Here I take N1 and V1 to be constant. Here I take N2 and V2 to be constant. And in principle I should take a derivative with respect to this parameter here. So this is delta U1, delta S1 by delta U1, delta S2 by delta U2, and this is the energy du1 and du2. Okay. So now I am saying that at equilibrium, this quantity must be 0 because ds is 0. Now what is this du1 and du2? First of all, because the total energy is conserved, the energy that the first system loses must be gained by the second system. So du1 must be minus du2. Okay. Let me just call this du. So this implies that du times delta S1 by delta U1 at constant V1 and N1 minus delta S2 by delta U2 at fixed V2 and N2 must equal 0. Which now, putting things back, is du times, this is 1 over temperature of system 1 minus 1 over temperature of system 2 must be equal to 0. Now this is true for any infinitesimal du. So the idea is we sit at the place of maximum entropy and say, let me exchange a little bit of entropy between this subsystem and that subsystem. If it's a true maximum, to lowest order, changing energy from here to here will not increase or decrease the entropy. So ds must be equal to 0. That's the definition of a maximum. Okay? If that is true, then this condition must hold for any du or whatever it is. If this is true, if this has to be true for any du, therefore this quantity must equal this quantity, which implies, just a sec, that T1 must equal T2, which must be equal to the common temperature T. So we said, let us say there is some system U1 and U2 here. I now allow them to exchange energy until finally it reaches some state of maximum entropy, in which, let us say, there is U1 energy here and U2 energy here. I want to determine the factors governing those states. So I say, in that state of maximum entropy, ds must be 0. That is, entropy should not change if I further transfer a little bit of energy from some subsystem to another. Okay? This is the property of a maximum. The first derivative of the entropy with respect to the energy must be 0 at that maximum, and the second derivative must be negative because it's a maximum. It's a function that basically looks like this. So here the slope, which is this first derivative, must be 0, and the second derivative, which is how much it turns, must be negative at the maximum.
So, in the case, this is extensive properties, right? Energy. So, when we are allowing the energy to move from one system to other, considering the whole system, it must be sum, the total energy.
No, whatever. Remember that U1 plus U2 is a constant. That means U1 minus U minus, say, let's say du plus U2 plus du must be the same constant. So whatever energy, so now the system has U1 minus du, the system to the right has U2 plus du, but the total energy is still fixed. So it's only the internal constraint that they're not allowed to transfer energy. That's what I'm relaxing. So now my system has settled down, and I'm settled down to the state where the entropy is maximum or ds equal to 0. Once I'm in that state, any further transfer of any small amount of energy from one to the other, the ds corresponding to that must be 0, because that is what I mean by the fact that I'm at a maximum. If ds must be 0, this is d of S1 plus S2, because S is just S1 plus S2, it's just it, which is the same as ds1 plus ds2 equal to 0. So ds1 is delta S1 by delta U1 times du1. ds2 is delta S2 by delta U2 times du2 over here. These derivatives, because S1 depends upon 3 parameters here, when I ask about the change of S1 with respect to one of these parameters, I am saying automatically that I keep these 2 parameters fixed. This is the same as saying that you can exchange energy, but you cannot exchange particles or volume. So this is the way I write the first term here. This is the way I write the second term here. Now I worry about one more thing, that if I transfer an energy du from here to here, and the du that is lost from here must be gained here. Okay. So the change of energy of system 1, du1, is minus the change of system u2, which is minus du2. So if I call this du1 to be du, then du2 is minus du. Okay, it's because what energy one system has gained has been lost by the other system. So now I just put this back in here. So this now becomes du into delta S1 by delta U, delta U1, and minus delta S2 by delta U2. But now I know what these is, because by definition delta S by delta U at fixed B and N is the temperature. So this will be 1 over temperature of the first part, 1 over temperature of the second part of the second little block. But now look at the cleverness of the argument. Now it says that this must be true irrespective of what the du is. It cannot depend upon the du. Du is something that's in my hand to choose. I've just moved, say, 1 microjoule of energy from one to the other. If that is true, if this must always be 0, the only way that can happen is this quantity itself is 0. If this quantity is 0, that means T1 must equal T2, which is the common temperature. So this is a roundabout way of saying what is sometimes called the first law of thermodynamics. There are two objects that are in equilibrium with each other is in equilibrium with anything else at the same temperature. So now that these are in equilibrium, there is no further exchange of energy between them will increase the entropy. So the third way of saying this is the state of maximum entropy corresponds to the state in which the temperatures of both these subsystems are the same. This also agrees, remember, with our with intuition. If we take the final state of this coffee cup is a state in which the temperature of the cup is the same as the temperature of the room. They are now in thermal equilibrium. So the fact that thermal equilibrium corresponds to having the same temperature is a part of our own experience, and this is essentially codified in this result here. Suppose we are not in equilibrium. So suppose we are close to but not in equilibrium. Okay. Then ds is certainly not 0, ds is greater than 0 because it's still increasing. ds is final entropy minus the initial entropy, the change in entropy. But this must be positive because I'm going from a situation of smaller entropy to a situation of larger entropy. Okay. Therefore, let's go back there. 1 over T1 minus 1 over T2 times du must be greater than 0. Okay. If T1 is greater than T2, then 1 over T1 is less than 1 over T2, which means that this quantity is now negative. If this is negative, then this quantity must be negative if this is to be positive. What does this being negative mean?
It's the other way around.
Means is the way I've written the sign is the other way around. So system 1, let me just draw this picture again. System 1 loses energy to system 2. This is the direction of the flow of energy. Okay. So if I'm not in equilibrium, I'm a little away from equilibrium. The way I will move towards equilibrium is if the system at larger temperatures loses energy to the system at lower temperatures. So this determines the flow of heat. So your cup of coffee always cools down. It never heats up. So already we are seeing very interesting things here. But first of all, we are able to get from the requirement that entropy is maximized, the requirement that systems are in equilibrium, in thermal equilibrium with the same temperature when that entropy is maximized, when they are allowed to exchange energy between each other. And from here what we found is that if the system is going towards equilibrium, consists of two different paths, one at a higher temperature, one at a lower temperature, and they are allowed to exchange energy between themselves, then heat energy will always flow from the hotter system to the cooler system. Okay. So this is again a very important and interesting result that comes just out the way we have formally written all of these answers out. Okay. So now let's just go back to one thing that we wrote the last time. We said that if we had S as a function of u, v and n, and S had certain properties with respect to u, mainly that it was monotonic and increasing and smooth and continuous. Then instead of S of u, v and n, I could exchange this to get u as a function of S V, and N. Okay? So it's essentially saying if I have a function that looks like this, where for every value of u I have some value of s, I can exchange that so that this becomes here, and I can write as s as a function of u. I'm always able to invert this relationship. Okay? So now let us write ds to be, du to be delta u by delta s at fixed v and n times ds plus delta u by delta v at fixed s and n times dv plus delta u by delta n at fixed s and v times dn. I'm just expanding this particular u as a function of s, v, and n by a small amount. So this says if I change s to s plus ds, plus ds, v to v plus dv, and n to n plus dn, the total change in this function and this function between both of these is just given to lowest order by this partial derivative expression. S depends only upon these three parameters. So here u is a function of s, v, and n.
U as a function of s will also be increasing monotonically, or it will be different?
You can see from here that it has to do the same. It also has to increase. This says it's single valued here. So whatever, it's as though I have plotted this on this axis and this on this axis. Okay. All right. So now we can put different parts of this back in. So this quantity is now the temperature, because delta S by delta U at fixed V and N was 1 over temperature. Delta U by delta S at fixed V and N must be the temperature itself. This is a standard result that follows from partial derivative. So this is T times ds. And now we have to worry about these additional factors here. So these are defined to be the following. This quantity here is defined to be a quantity which is minus P. And this quantity here is defined to be the quantity mu, or the chemical potential.
That was a definition, right?
This is a definition, so I will just write out this definition. TdS minus P dV plus mu dN. This is du. The sign of this particular expression is chosen for a specific reason. That is, if, okay, so I'll just describe that reason a little later, but let me just write this expression down for you. This defines a quantity called P, which is to be identified with the pressure, and it defines a quantity called mu, which is identified with something called a chemical potential. So I mentioned pressure, temperature, chemical potential in the beginning, but these are the ways they are defined. So I define the pressure as a change in the energy with respect to the volume, minus sign outside, at fixed number of particles and at fixed entropy. And I define the chemical potential as a change in the energy with respect to the number of particles at fixed entropy and at fixed volume. Another way of writing it, which you will see in thermodynamics books, is du is dq plus dw plus dwc. And sometimes we will also draw a line through these things to indicate that these are not exact differentials, but an exact differential. We won't worry about that. Just look at this term. This term here is just t times ds. This term here is minus P times dV. This term here is mu times dN. This is called the chemical work. And this is called the heat transferred. And this is called the mechanical work. So this equation here, which is just a translation of this equation to slightly different languages, says the following. I can increase the energy of my system by transferring heat to it, making this, heating it up or allowing it to exchange energy with some environment that is at a larger temperature. I can do work to it, I can compress it, for example, or I can change the number of particles, which is another way of doing work on and changing the energy of the system. Okay? This is the most general way of writing it, and it also corresponds to physically what we know. We know that by compressing a gas, for example, and by changing the volume of that gas, I am doing work on it. I compress it. Now, if I release that compression, it will expand out and push outward. We are a little less familiar with this, but whenever we discuss chemical reactions, the nature of chemical work and how the chemical potential behaves will be very important in what we do in the future. And in fact, a lot of when you write down equations, systems of biology representing chemical reactions, compute reaction rates and so on, those will be related to quantities like the chemical potential in very specific ways. So it's important to understand where this comes from. The part that you may not have seen earlier is this part. This is the part that says there is a heat transfer associated with an increase in entropy of the system, TDS. Okay? And this T, in a sense, is a handle by which you allow for heat transfer from one to the other. The sign of this is positive if work is done on the system. And this accounts for the fact why dW was written as P times dV with a minus sign here. The reason is, if I take my system here and I now compress it, I have changed the volume. The volume change is negative because it has started off large and became small. In order to compress it, I've had to do work on it. I put work into the system, increasing its energy. Therefore, this quantity on the left should be positive. The pressure is positive, it's pushing inward on the system. So positive times a negative quantity with a minus sign outside gives you a positive sign here. That's why the sign is chosen this way, to be consistent with our own physical intuition regarding how to count the sign, what is the sign of the work done on the system. Positive work done on the system increases the energy of the system. If you allow the system to do work itself by expanding, that decreases the energy of the system. It's called a chemical, it's
Why potential?
part of it is just historical accident of what these terms were called, but the other part of it is also that you can alter the chemical potential for molecules that are charged by changing the actual electrostatic potential, by putting it in an electric field. For example, this controls the flow of particles from, say, one part of the system to the other. If your particles are charged, one way of making them flow is to put an electric field that pushes them in that direction. So those terms also enter a chemical potential of this form. That's why the word potential can also be very roughly used for things like this. But the actual roots of this are more in historical terminology. So this is one very fundamental relation about what the different contributions of energy are. Earlier, before thermodynamics, we tended to ignore this part of it. We said, oh, everything is mechanical. We even forget about chemical. If I do work on a system, I increase its energy. Now we realize that there are ways of transferring energy to the system. They don't have to do with doing work on it. It's just allowing energy to flow and increasing the entropy of the system. So this is that part of it that allows for the transfer of heat to the system, changing its energy. This is the part that allows for doing work on the system, on some mechanical degree of freedom of the system, like its volume and changing its energy. And this is the part that says chemically if the number of particles, of different species of particles inside the system changes, then by just changing that number, I can change the total energy of the system. So the next time we will do maybe a little more of this. We will do something called Legendre transforms, which is a kind of clever way of changing this fundamental relation, making other forms of that fundamental relation. And then we will try and motivate statistical mechanics and how to understand what is the entropy from the point of view of statistical mechanics. So, I am essentially compressing what would be about 6 to 8 lectures into just very, very brief selection of different topics, because you do not really need to know more than this, but I would like you to go back and think a little bit about these things. The way we set it out as postulates. It was very clear what we assumed, what the consequences of that assumption were, and how we wrote them out. And because of that, we could get very clean division between the heat transferred, the work done, and the chemical work done. But these are all very difficult and deep ideas that took many, many centuries to develop. So go back and think about it.